Hi all, welcome to another session from Nairo Research. I'm Sridhar here. So in this session, we are going to discuss about the applications of reactive force field engine. So diffusion coefficient in battery modeling. So we have already taken a webinar on this topic, but how this module can be useful, or what are the different engines which can be useful for battery modeling? That's the main content of this upcoming videos. So let me start with the diffusion coefficient in battery modeling. So in battery systems, the diffusion coefficient quantifies how fast the charge carriers, typically lithium or sodium ions, which move through an electrolyte or interface. So it directly controls the rate capability, polarization, capacity fade, and charging or discharging kinetics. So depending on the length and time scale, diffusions can be solid state diffusion, which can be briefed in electron materials like bulk and along specific crystallographic directions. Interfacial diffusion at electrode, um, focusing on electrolyte boundaries. Liquid phase diffusion in electrolytes or binders. From a modeling perspective, diffusion can be, or diffusion coefficient can be intrinsic, which is chemical or self-diffusion, or effective or apparent diffusion. So depending on whether the concentration, gradients, defects, and microstructures are explicitly included. So how diffusion coefficients are computed in Amsterdam Modelling Suite? So AMS supports multiple complementary rules covering ab initio to mesoscale regimes, very suitable for battery material research. So first one is DFT-based diffusion, which is best for the solid electrodes. Example, lithium diffusion in cathodes or anodes. So the method is first we need to optimize the bulk structure either with the periodic DFT engine. We need to identify the initial and final ion sites. When we use the NEB methodology to compute migration barriers, then we need to convert barrier to diffusion coefficient using a linear relation. So what are the tools which we can, what are the different tasks which we can use to perform this calculation is first we need to optimize the lattice, then we need to perform the NEB calculations, the vibration analysis, which will be optional for pre-factor refinement. So the second methodology is the ab initio molecular dynamics, which we can perform using DFTV and reactive force field, best for finite temperature diffusion, including lattice dynamics, the methods. We need to run the dynamics at target temperature. We need to track down the trajectories, compute the means for displacement. Then we need to extract the diffusion using Einstein relation. So we can perform the calculations using either band or DFTB and classical MD. Of course, we can use reactive force field or force field engines. Best for long time or large system interfaces and electrolytes. We can use reactive force field or classical force field to run nanosecond scale MD to compute MSD for analyzing the diffusion coefficient. And then KMC, kinetic Monte Carlo simulations for multi-scale diffusion. Best for bridging DFT barriers to microscopic diffusion. So these are some of the important applications when it comes to AMS for battery modeling. So why AMS is particularly strong for battery diffusion studies? The seamless DFT MD analysis workflow, the accurate localized basis set in the DFT codes for migration barriers, efficient DFTB for finite temperature diffusion, the built-in MSD and transport analysis, the strong support for periodic materials and interfaces. So when we choose the right approach for battery context, so the crystalline cathode or anode, we can, the methods recommended in AMS is band plus the NEB task, and solid electrolytes, the DFTB or band with AIMD. Liquid or polymer electrolyte, we can use classical MD. Interfaces and other electrolytes using reactive force field MD, and long time transfer, we can suggest DFT plus KMC. So these are the different methods which we are going to discuss in the coming videos. So as an introduction, I would like to say that this is actually a base level briefing about how diffusion coefficient in battery modeling can be performed using Amsterdam Modelling Suite. Thank you. We will see in the next videos with a brief outline about how we can do the calculations from optimization to molecular dynamics. Thank you.